UCSD, and I would love to physically visit UCSD, but it's not possible at the moment. But at least I can be virtually here back to UCSD, and my recent research work aim looking for some collaboration with somebody or some institute. And let me start. So I'm going to talk about enabling picosecond level time synchronization for inexpensive IoT devices. And again, I'm from NICT, Japanese government lab working for ICT type of research. So I'll talk about biography and technology application and so on. And so let me start with a little bit of my introduction. So after I graduated the university in Tokyo, I joined the UCSD PhD course in physics. And this is, well, my thesis advisor, Fred Driscoll. And this is the senior researcher who had been a mentor for 6 years for me. So I literally learned everything from them. And I was working on the plasma physics, experimental plasma physics. This is a picture of Penning-Molenberg trap that holds the ions or electrons with the magnetic field and the electric field combination of them. So I spent 6 years, great years in UCSD, and then after I graduated, I went to Alaska Fairbanks working on the, instead of experimental or indoor plasma, we studied the outdoor plasma on the aurora borealis. We used the aurora or the plasma for the communication purpose. And anyway, so we played around with the aurora borealis or northern lights. And then after 1 year, I moved to NICT Boulder, and there I went back to sort of trapped ions. So instead of plasma, now they call it trapped ions. And we use trapped ions for the quantum information purpose. I was joining the David Wineland's group, who won the Nobel Prize in Physics in 2012. And then after that, I moved back to Japan at NICT Tokyo. And I was in the team to build a neutral atomic clock, using strontium as the optical lattice clock. That's one of them. And I also started working on making our own ion trap type of atomic clock. Now, but 5 years ago, actually, I switched my research topic completely from atomic clock to the synchronization using the radio communication or wireless communication devices. That was a huge change for me, but I believe it's worth doing it. It was really easy and cheap way to bring the synchronization in this IoT era. Now let me spend 2 minutes to introduce my institute. So again, this NICT stands for National Institute of Information and Communications Technology. And they do actually a wide variety of researches. And basically, it's based on ICT research, but we also make and deliver the Japan Standard Time. And we also do the space weather forecast, meaning how much heat or alpha particles are flying from sun to earth kind of thing. And it's deeply related to the aurora borealis, or it can affect the GPS signal. And also, we are focusing on cyber security, and we are doing the training of people as well. And on another side, we are also have the function of funding as well, rather than just doing research and development. And it's headquarters in Tokyo, and it has about 1,000 people working. And then now, starting in December, I joined the Silicon Valley Research Hub in Sunnyvale, which is near the San Jose airport. And our objective is the global development of research and development outcomes. So I want to collaborate with somebody or anybody who is interested. And so just to give you a brief idea, we are doing researches in various directions. One is like big data type of analysis. And we're also doing the sensing using the radar or millimeter wave. And so we are doing the remote sensing measurement or using the space and doing the environmental measurement. And also we are doing the integrated ICT, meaning we are sort of working the wireless network technology or with the wired network technology as well. And we are also working on the cybersecurity. So if you are interested, please contact me. And this is another sort of cutting dimension, but it's basically saying the same thing. We have various researches going on. Okay, now I'm going to talk about my research topic that I have been working last 5 years. And the topic is about space-time synchronization. And what I mean by that is we want to, before that, I want to sort of share our vision, and it is to establish an environment where the precise space-time synchronization is readily available. And we believe that helps us to have the better human interaction. And so what I mean by space-time synchronization is in the local area, meaning where the wireless communication is sort of available, all the devices are synchronized, and also the position of each devices are mutually recognized. And that kind of thing was probably difficult 20 years ago, but now it's fairly easily available. So let me share how we are going to do it. So when I say space and time, it's sort of separating two concepts, but in terms of synchronization, it's actually cannot be separated. What I mean by that is, let's do some Gedanken experiment. And suppose you are in a room and you are looking at the clock at the wall, and two people wants to synchronize their wristwatch to the clock on the wall. And the question is, how well do these people can be synchronized to the clock on the wall? And the fact that I'm asking this question sort of indicates that with this method, you cannot completely synchronize the clock in theory. And the problem is that it takes time for the information to travel, meaning the right clock information or time, it takes about 3 nanoseconds to reach 1 meter away. So this person in blue, at best, he can synchronize with the 3 nanosecond delay. And if you are 2 meters away, it's going to be 6 nanosecond delay. So if you want to precisely synchronize your clock, then you need to know the distance from the clock and compensate for the distance or delay of the information. And this is what I mean by the space and time are not separable. Now, as I mentioned, we are in charge of setting time for Japan Standard Time. So it is very crucial mission for us to check if our clock is right in terms of UTC, for example. And for that purpose, we are supposed to compare our clock to the German clock. Now, the way we do, in order to do that, there is an existing well-established technology called two-way satellite time and frequency transfer. And this technology works like this. So from Japan, we send a clock signal on millimeter wave and send it to the Germany. And between there is a satellite to transfer. Now in Germany, it records the clock signal and compare it to the German clock and record the difference as a delta T Germany. And this delta T Germany, of course, the meaning of it is it has the time difference, clock difference between Japan and Germany, of course, but it's have the added propagation time, P. So unless you know this propagation time, you cannot compare the clock precisely, like in the previous example. So in order to compensate for that or measure the P, what we do is from Germany, they transmit the clock signal as well and send it to Japan. And in Japan side, they record the time difference between transmitted clock and their own clock and record it as a delta T Japan. And the meaning of it is it has the clock difference with the opposite sign viewed from Germany because the viewpoint is opposite with the same propagation time P. Now, since if you have two measurements together, actually you can separate the clock difference and the propagation time. If you add the both measurements, then the clock difference cancels out and you are left with the propagation time, P. And if you subtract two measurements, the propagation time cancels out and you are left with the clock difference. So this is the essence of the two-way satellite time and frequency transfer. And it's proven that it can compare the clock at picosecond level. And we have been using this technology for 15 years. Now, what we did is, well, do we have to really use that satellite? And can't we just use the commercially available wireless module to do the same thing, to do the picosecond level of time clock comparison? And so what we did is we applied the same protocol into the commercially available wireless communication devices. And I mean, we did prove that we can do the picosecond level of synchronization. And another interesting thing is now the propagation time, it can be measured as well. And if you multiply the propagation time with the speed of light, then you get the distance. So it can do the distance measurement in between modules as well. And we named this technology wireless two-way interferometry, picked WI and WI here, and we call it YY. I forgot hyphen here. Now, the way our research progressed was we first made a combination of equipment, and we used PC and the commercially available transmitter, which was we tried 2.4 gigahertz Zigbee, and also we tried 920 megahertz, that is frequency shift keying, and Zigbee is the QPSK, and used software-defined radio as a receiver, and then.
Dr. Shiga?
Yeah.
Can I, sorry to interrupt, can we record your talk?
Sure. Please go ahead and you can record it.
Okay.
Okay, so the first experiment was in combination of having a rubidium clock and the clock was sort of fed to the software-defined SDR, and now this experiment was successful, so we moved to making a module which now PC is translated to microprocessor, and the transmitter and the receiver are being, well, the function was held by the RF chip. And instead of rubidium clock, we used the custom quartz, and we made a module. So this is the prototype modules. And as a starter, we decided to use the 920 megahertz wireless communication module. And it's fully compatible with the IEEE 802.15.4. And that's because we just used the 920 megahertz wireless communication, and we asked chip maker to add a few lines to the digital circuit. And now this module can, this left-hand side or center one is our second generation model, which is up to 20 milliwatt transmitting power, which gives 100-meter range. And the third generation has high power, and also it has the Raspberry Pi in it just to record the data. Anyway, so this high power version goes up to 250 milliwatt, and then you can communicate up to 5 or more than 5 kilometers if you put it on top of the buildings. Now, this module can demonstrate basically two things. One, the first demonstration uses the part of the clock difference. So if you take the two measurement and subtract, you get that clock difference. And each module have the custom made sort of oscillator or clock. And we made the 10 megahertz out of those oscillators and put it in the oscilloscope. Now, if you look at it without doing anything, since the frequency of two oscillators are slightly different, so if one signal goes one way, but by pressing the button, it synchronized. And let me explain that again, because it is very quick. So even before pressing the button, each module is transmitting signal 13 times a second. So it's comparing the clock difference or measuring the clock difference 13 times per second. Now, when you press the button, it feeds it gives a feedback signal to the oscillator, so that the phase of the two will be synchronized. So it keep measuring the clock difference, and it keep feeding back to the frequency of the oscillator. Let me show it again. So it's already comparing the clock difference, so it knows how it's sliding away. And now by pressing the button, it tried to sort of phase lock, and now it's phase locked. It can do one more thing, that is by using the sum of two measurement, which is the propagation time. Now, propagation time is just plotted over here, and as you move the module closer, the propagation times goes down, and you back off, propagation goes up and down, and so on. Now, let me emphasize that we are not using PC, we are just using microprocessor, but since our calculation is whether you add or subtract, so this calculation is all done in microprocessing unit, and the PC is just plotting it out. And we made a sort of simple version of slightly network type, MAC layer, and now this is a star type of network. There is one leader, and there are 6 followers. And as you can see, the frequency, some are going right, some are going left, some are quick. But as you press the button, every module tries to lock to the leader. And you can see that everybody is phase locked at this point, and it stays like this forever. Now, so let me summarize the point of what we wanted to sort of demonstrate is that any wireless communication devices can be now become a precision synchronization devices by adding a few lines to the digital circuit of the RF chip and having fairly good the oscillator. And so again, this technology in now IoT is trying to make a connected world, but I think with the almost same devices, we can actually achieve the synchronized world to share a universal clock with everybody. Now, with this, I'm going to switch our focus to the possible applications. And application image, first of all, the number one is traffic control of wireless communication. Right now, we are sort of, our standard is well, the carrier sensed based, meaning if you listen carefully and if nobody is speaking, then you speak. But this method only works when it's not jammed. And now we are going into the sort of age that more and more wireless devices are being fed to the world exponentially. Now, with this technology, by knowing each other's position and time synchronization, and that allows autonomous distributed self-organization of the wireless communication traffic, meaning autonomously the devices can sort of coordinate with one another when to speak, when to listen. And also we are sort of envisioning that let's call it space-time authentication. I'll explain what I mean by that. Suppose you have 4 base stations in the buildings, like it's really happening with the femtocell. They are trying to put many base stations in the buildings. And suppose somebody transmits the signal and 4 base stations can receive it. Then what the system can do is by you doing the sort of reverse of GPS, the system can identify where the transmission was from and when it was. So for each transmitted signal, the system can label the space and time tag to the transmission. And that means rather than the transmitter trying to prove that he's right, but the system can use the space-time information as another layer of authentication. And in other words, if this was a sensor, the sensor just transmits the signal and the system can put the space-time label to the data of the sensor. And that additional data I think has huge value in order for the sort of AI or big data type of analysis. Another example is so now I'm moving on to more sort of detailed, solid example that we worked. So first example is the infrastructure monitoring. So what we did is we put one module on top of steel tower and the other on top of the solid building. And as we monitor the distance variation, we notice that every day the distance gets 2 centimeters less during around noon and backs off, and then next day it gets 2 centimeters shorter during day and backs off. So our interpretation of it is this tower is 60 meters height, but when the sun comes up and the south side of the steel structure was heated, then it actually hits more to the south side rather than the north side compared to the north side. And it expands on south side, and as a result, it tilts, the whole building tilts toward the north by 2 centimeters, like this much, every day. And so that was actually almost accidental. We were just testing the system if it can keep running for days, but then we realized that its distance is changed. Now, second example is sort of expansion of this finding, and what we did is on a helmet, we put 2 modules, and then we also added the prism. Sorry about the Japanese. And we set the 2 base or moving stations, and we monitored the distance variation to monitor the 2-dimensional position variation. And to check if what we are measuring is right, we use the laser rangefinder to identify the position of this helmet as well. So in this movie, my colleague is wearing the helmet with 2 modules on it, and here is 1 stationary module and another stationary module. So there are 4 modules in use. And as he moves around, this is with the YY and with the laser rangefinder, both of them are basically measuring the same position. And one additional bonus for us is that since we have 2 modules here, so it's not good resolution, but actually there are 2 points here, and you can sort of guess which way it's aiming at as well. And in the end, I mean, both of them are basically measuring the same result. But let me note one thing, that this method is working outside with not much things around. But we proved that this method needs to do, I mean, it needs to be upgraded or something. I mean, the same system doesn't work when in a reflective environment, like indoors, or when we put the metal walls and we surrounded it, and we found that it doesn't work. I mean, because of the multi-path effect or reflection. Now, this example 3, I was talking about the distance variation measurement, but this is sort of switching the viewpoint, and that let me move to this slide. So suppose these 2 modules are separated by 5 kilometers. And even though the distance doesn't change, but in between, it's not a vacuum. There is an atmosphere. And the atmosphere changes, and changes the temperature, humidity, and air pressure. And that causes the change of index of refraction of the air in between. And we found, well, we sort of knew that's happening, but we found that it's actually changing in result, it changes, we can view it as a sort of distance of change or distance of propagation time in between. So what we want to do with this technology, if we can afford, then is that by putting this type of mesh type of network in the area, local area, and try to measure the water vapor being concentrated at one place or not. Anyway, so what we did as a experiment is that we put 1 module at our institute, and we put another module at nearby or 4.25 kilometers away, but the tall building, it's a sort of radio building. And at 110 meters height, we put one and we put the other on top of a building. And this is the finding. So let me spend some time to explain this figure because it has a lot of information. Now, this on the vertical axis, we have the propagation delay or propagation delay in meter. So it's actually the propagation delay multiplied by speed of light. Now, instead of 4.25 kilometers being vacuum, since it has atmosphere, it looks about 1.3 meters longer than it is when you measure with the measure the distance with this radio. Now, having said that, that delay can vary depending on the status of the atmosphere. And mainly it's affected by the amount of water vapor it holds. And you can see that some days it doesn't change much, but on some other days it changes the distance by 10 centimeters. The one division is 5 centimeters in this scale. Within one day it goes up. I'm sorry, so the horizontal axis is one division is one day. So within one day, it goes up by 10 centimeters, goes down by centimeter, and backs again to centimeter, and then go back. So some days it fluctuates a lot, and that can be measured. And this red is measured by our technology, wireless interferometry. And blue and green is only the estimate that we can do at our best, and that is done by measuring the temperature and humidity and atmospheric pressure. We can make a good estimate of the index of refraction at microwave range. Now, we can only do the point measurement of those meteorological measurements. So if you assume that the whole atmosphere is represented by NICT side, then you get blue line. And if you assume that everything is represented by the other tower side, then you get green line. And what we measure is something in between. So what we are measuring is in between those two lines. So I think we are fairly confident that what we are measuring is actually the right thing. Now, let me move on to another example. Now, it's not a done experiment, but this is just the idea that we have been discussing. And with the phased array measurement, you have many elements. And for those elements, if you use millimeter waves, you need to have picosecond level of synchronization. And traditionally, that is done by connecting from a single clock with many wires with the same length. And so if you want to do this kind of measurement in space, you need to bring this whole thing up to the space. Now, the weight of these lines are not, I mean, that's actually adds up a lot because typically they want to put like 10,000 modules or 10,000 elements. That means you have a line of 10,000 equal length lines. And with this technology, you can eliminate those weight. And also the lines can be cut in process of expanding this array. So that's one idea. And another idea is the sort of grid type of application. The synchronization of the grid elements are crucial. And of course, we shouldn't depend on single method, but I think we can add another layer of synchronization for the more added security. And the last one is very conceptual, but this is what we are envisioning. So suppose, I mean, let's take a look at the 3D printers. And this 3D printer is really limited by this wall. The size of the material you can make is limited by the size of the box. But if this space-time synchronization really works as we envision, then we can basically make any size. Of course, you might be limited by the height, but you can basically make any size or width of the material. And of course, you can also envision the several robots work collaborating together. And that's what we are aiming at. So in short, the world is, with the IoT vision, aiming toward connected world, but actually with a little bit more of the sort of investment, we can achieve synchronized world, we believe, and that's what we are aiming for, and that's crucial for the machine-to-machine interaction and machine-to-machine sort of collaborations. So this is the summary. We have demonstrated the feasibility and cost effectiveness of space-time synchronization module. It's really almost made by the same price for the wireless communication devices, depending on how well you want to do the synchronization. If you want to do well at picosecond level, you need to have the better crystal, but it depends on how much precision you require. And also, space-time information adds high value to sensors, meaning sensor data is now tagged with space-time information, having a lot of more information and make it easy for the mass sort of data analysis. And the synchronization affects the performance of the 5G. And now we all know that in 5G, the synchronization is becoming sort of crucial, and it's almost becoming a bottleneck of the applications. And also, we say that the distributed and coordinated base station synchronization is please give me 1 minute to sort of introduce our research group, Space-Time Standards group at NICT. We are making the atomic clocks, cesium atomic clocks and strontium optical atomic clock, and we are sort of disseminating the Japan Standard Time, and we are comparing our JST to UTC, and also we are sort of developing this synchronization technology. And so, well, this is end of my talk, and we are really searching for opportunities for collaborations with the research or deployment. And if you are interested, please contact me. And thanks a lot for your attention. And I'm ready for the questions.
Thank you. Let me unmute and allow people to ask questions if they have. Okay. So,
I mean, there's no way that we could do this and not give the confidence of
Professor Rao, are we allowed to ask questions?
Yeah, I think so, but I think people need to be careful to keep their microphones off if they're not talking. Okay. Yeah, please ask questions. Yes.
Okay. Okay. Hi, my name is Raghav. Thank you, Dr. Shiga, for this wonderful presentation. I work with the WCSNG group with Professor Dinesh Baradia, and we do a bunch of stuff in like wireless localization and with millimeter wave and things like that. So it's very relevant to whatever you discussed right now, and like we're quite excited to see the kind of applications that you have come up with and tested. So we have a few questions. So am I right in describing the solution that you've built as some sort of over-the-air disciplining of the oscillator?
Okay, yeah. So we call it phase lock. but you're talking about the sort of I think what you meant by discipline is the fact that we are feeding back to the frequency of this follower module to match the master module's frequency. So with this technology, basically we don't care the leader's frequency is right or wrong, but we just follow the leader's frequency blindly.
Yes, understood. And this is being done just by feeding the time differences between these two modules. Is that it?
Yeah. So one thing I would say is this is a frequency being controlled to adjust the phase of the clocks. So it's like two cars are moving and you want to align the head of the car, and you being the follower, you either step onto the gas or release the gas and then sort of trying to match it. So you are not jumping the phase to match, but you are controlling the frequency.
Got it. So is there like a continuous transmission and reception between these two modules, or is it discrete? If so, how many times do you do it?
Yeah. That's a good question. So at the moment, we are comparing like in this demonstration, it's done 13 times a second. You compare about 13 times, but it depends on how much synchronization precision you want to have. And if you wait longer, the crystal will free run and you drifts away more. So if you want to, the frequency of the measurement, it really depends on your application.
Got it. Understood. And yeah, sorry for taking so much time. I just have a last follow-up question.
Okay.
Thank you for your time. So you had mentioned toward the end that to get picosecond level of accuracy, you would need better crystals like rubidium crystal or something like that. Is it just to get an absolute picosecond accuracy, or can we get picosecond level accuracy between the two modules in the setup you're showing?
Okay, yeah. That's a very important question. So what I mean by picosecond level is actually, in precise wording, it's picosecond level of stability. And the precision is actually divided into the stability and the absolute sort of frequency. And so in this application, we don't care about the frequency being right. But as long as if the crystal have the capability of holding the right frequency, then we call it the stability. So since our goal is to lock to the leader frequency, or leader's phase. So as long as it can hold the same frequency for a given amount of time, then that's all we want. So what I mean by good crystal in this sense is a very stable crystal.
Yeah, understood. Thank you.
Okay, any other questions? Okay, I guess not. So thank you, Dr. Shiga. We appreciate it, your talk. And I think I'm going to bring the meeting to a close.
Okay.
Thank you.
Okay, thank you. Well, thanks again for your time. And please contact me if you have further questions.
Thank you very much.
Thank you, Dr. Shiga.
Thank you.
Thank you.